sequences come from? Well, they're not just manifested by sequencers. Instead, they're produced by recording patterns of intensity over time, typically fluorescent intensity, as a function of time. Now, what I'm showing you here is an example from a Sanger sequencer, kind of the old type of sequencer today. This is produced by a capillary electrophoresis fluorescence measurement of the complementary strands being produced, being polymerized for a template strand. If you were to look at the region around nucleotide 200 in this electropherogram, you would see patterns of intensity that are nice and regularly spaced, and you see that what letter should be called for each position is pretty unambiguous. We have a few places where the black fluorescence is at the peak. Those represent G. We have places where the red peak is highest. That's a T. Green for A, and blue for G. All fairly straightforward. We do, however, see that when we get to very high parts of the sequence, when we get to the end of the sequence, we find that the peaks are no longer baseline resolved from each other. The signal no longer dives all the way to the base before coming back up again. As a result, there's some ambiguity about how many A's you might find at this position, near 720. So, when we look at a sequence like this, it's probably going to be the case that we're going to knock the ends off of this. After all, nothing before about nucleotide 50 is really worth writing home about. And we see that the stuff above 700 nucleotides is probably going to be a little bit dubious as well. But we'd really like a finer-grained approach of being able to assign a base call, which is to say a letter read from this electropherogram, and to evaluate the quality of that individual base. Now, Phred was software that was created all the way back in the 1990s by the group of one of the members of my PhD committee, Phil Green. So Phred is designed to estimate base calling errors when working from electropherograms like this. So once you've got a sequence associated with an electropherogram, you need to be able to put a probability of error on each position. So I'm going to talk about three different properties that we expect for the quality of a particular location to be really solid. The first of these has to do with the beat of the sequencing calls. So let's look back at our electropherogram for a minute. If you were to write the exact moment at which each peak hit a maximum here, you would think of this as sort of a timeline, and we've got a beat showing up at more or less regular intervals across this space where each die comes to a maximum. That's really good, because it means that that regular spacing is something that we attribute to high quality separation of sequence and a greater confidence that the base calls we attribute to that are real. It uses a technique called Fourier transform as a way to ascertain what the optimal beat is and to lay out its map of where it anticipates that each signal should come to a maximum. So having a peak matching the beat of the surrounding region is a very strong vote in favor of a particular peak being a real base call. Next, we want to see that only one trace is concave down. Now, we could talk here about the second derivative of the overall intensity signal, but I don't want to lose everyone, and it might be after lunch, so you never know. So let's talk then instead about concave down as being an arc that has a maximum value in the middle and touches down to the baseline on either side. So we want to see that of the four traces that might be up here, red, green, blue, and black, only one of them hits a maximum at this point. If you had two different colors that were each hitting a maximum at the same time, then you might think, well, it could be this letter or it could be that, and we don't want any competition like that. Instead, we want to see that these different letters, that only one of them has a good peak at a location. And finally, we have this highly probable errors are far away aspect, which is to say that if you have a base call that's pretty dubious, well, the base calls on either side of it are going to have their scores marked down as well. If you're 5 nucleotides or 10 nucleotides away, well, then you might start having a score that's essentially unaffected by this bad peak call. that might seem kind of prejudicial or unfair. But I want to give the example of the house that I lived in Nashville. When I first moved there, I bought a house in a neighborhood that was rapidly gentrifying. In this case, the house that I lived in was once a drug dealer's house. Yeah, people would come by and buy drugs right off the stoop at this house in Nashville. Well, the neighborhood had gotten really sick of this, and part of the reason was that when they tried to sell their houses, the realtors for the buyers would look down the street and say, look, there's this drug den right down the street from there. There's not a chance you want to put an offer down on this house. Well, in the same way, when we look at base calls for a particular electropherogram, if you're right next door to a base call that's highly in doubt, it's probably going to cast a pretty big shadow on these neighboring nucleotides as well. So being farther away from them gives us greater confidence that this error, this probable error over here, is not going to impact this peak that's some distance away from it. Now, bioinformatics very frequently uses the concept of negative log scoring, and I want to try to explain how that works out. In this case, we want to really maximize our ability to detect very rare events. So most of the sequencing base calls that we're actually going to care about have a base call score, a Phred score, better than 20. So I want to explain how that works out. If we have a probability of error of 0.01, that's the same as saying we have a 1% chance of error at this location. But let's write that in scientific notation instead. So 1e minus 2 translates as being 1 times 10 to the minus second power. So 10 to the minus second power is equal to 1 out of 100. So 1% in Phred world is written as a Phred score of 20. A 1% chance of error equals 20. So 1 times 10 to the minus second, let's just plug it into this expression up here. We plug in 1 times 10 to the minus second as p. Log base 10 of 1e minus 2 is minus 2. So minus 2 multiplied by negative 10 is 20. So hopefully the math is mostly straightforward. I realize that thinking in log terms is going to be unfamiliar for a lot of students, but bear with me. We would write a 1 out of 1,000 chance of error as a p of 0.001, which is the same thing as 0.1%, which in scientific notation we would write as 1e minus 3. So we already said that when we take the log base 10 of these numbers, you basically just strip off everything and keep the exponent. So log base 10 of 10 to the minus third is minus 3, times minus 10 is 30. And finally, for this slide, we see that 1/100th of a percent is the same thing as 0.0001 and is equal to 1 times 10 to the minus fourth power. So to compute the Q score, the Phred score for this number, we simply take the exponent, minus 4, multiply that by negative 10, and that gives us a Q score of 40. Okay, so in the linear domain, 20 and 30 don't look very different, really. But we have to remember that those are scaling with the log of the probability. So a Q score of 30, if you have a stretch of nucleotides that have an average score of 30, they are 10 times less likely individually to be an error than a similar stretch of sequence with an average score of 20. And having a set of nucleotides with a Q score of 40 average have 10 times less chance of probability per nucleotide than does a similar stretch with an average Q score of 30. So even though they look even though a 20 versus a 30 doesn't seem like that big a deal, it's a 10-fold difference in the amount of error we estimate here. Which brings us finally to FASTQC. FASTQC is some software that's intended to look at these Phred scores at a very large scale. So first off, what is a FASTQ? A FASTQ is a file of raw sequence produced by a sequencer. Typically, we find these being generated by next-gen sequencers. So if you have millions and millions of sequences all being output by this sequencer, they're all going to get dumped into a FASTQ file. FASTQC reflects the fact that these sequences are not by themselves. For every stretch of 40 nucleotides or 72 nucleotides, we also have a set of 72 Phred scores coming alongside that. And those are all included in the FASTQ file. So FASTQC is able to look into these and ask questions like the one that's illustrated here, which is to say, how far into each sequence can I go before typically encountering errors? So here we're looking at the average quality score for nucleotide 1, where the median is 40, which is to say it has a 1 in 10,000 chance of error. In fact, we can go all the way out to nucleotide 50 before we start seeing that a probability of error yields a Q value of less than 38. So this is a pretty good sequencing run. That said, occasionally we see that the base call at position 50 dips below 20 for some set of sequences. So FASTQC is giving us a notion of how confident we can be about individual base calls across the body of the sequences that we've produced. So the FASTQ is output by the sequencer, and it includes base calls and Phred scores, quality scores. FASTQC lets us evaluate these quality scores in the context of lots and lots of the reads produced by the sequencer.